AdaBoost, or adaptive boosting, is a powerful ensemble learning technique that combines multiple weak classifiers, such as decision stumps, to create a strong classifier. It was introduced by Freund and Shapier in 1996 and is widely used for classification tasks. The key idea behind AdaBoost is to iteratively train weak classifiers on weighted data, adjusting the weights to focus more on misclassified examples. AdaBoost is one of the earliest and most popular boosting techniques, forming the foundation for many advanced methods. AdaBoost trains multiple weak classifiers in sequence, where each classifier tries to correct errors made by the previous one. After each round, misclassified samples get more weight, so the next learner focuses more on these difficult cases. At the end, all weak learners are combined using a weighted sum, like a voting system where better learners get more say. Misclassified samples receive higher importance to ensure tough examples are handled better in the next iteration. The final AdaBoost model is the combined strength of all weak learners. If a weak learner misclassifies certain samples, AdaBoost increases their importance, making future learners focus on them. Each new weak learner works harder to classify difficult examples correctly, adapting the model to the data. Correctly classified samples get lower weights, so the focus stays on reducing errors rather than overfitting on easy cases. Let's understand and break down how AdaBoost works, step by step, with intuitive explanations and mathematical insights. Let's get started. Here is our dataset. We have 7 samples, each with a feature X and a label Y. The label is either +1 or -1, representing 2 classes. We start by assigning equal weights to all samples. Since there are 7 samples, each weight is 1 divided by 7, which is approximately 0.1429. Now, we train our first weak learner, which is a simple decision stump. It splits the data at x equals 2.5. If x is less than 2.5, it predicts +1. Otherwise, it predicts -1. Here are the predictions of the first weak learner. It correctly classifies samples 1, 2, 3, 4, and 7, but misclassifies samples 5 and 6. Next, we calculate the weighted error of this weak learner. The error is the sum of weights of misclassified samples, which is 0.1429 plus 0.1429 equals 0.2858. Now, we compute the weight of this weak learner, called alpha. Alpha is calculated using this formula. For our weak learner, alpha is approximately 0.4581. Now, we update the weights of the samples. Misclassified samples get higher weights, while correctly classified samples get lower weights. Here are the updated weights before normalization. To normalize the weights, we first calculate the normalization factor Z_1, which is the sum of all updated weights. Here, Z_1 is 0.9035. Finally, We normalize the weights by dividing each updated weight by z_1. This ensures the weights sum to 1. Here are the normalized weights. We repeat this process for more weak learners, updating weights and computing alpha at each step. After training multiple weak learners, we combine them into a strong classifier. The final prediction is made by combining all weak learners using a weighted vote. If the sum is positive, we predict +1. If negative, we predict -1. And that's how AdaBoost works for classification. By combining many weak learners, each of which is just slightly better than random guessing, we build a powerful final classifier. The weak learners focus on different parts of the data, especially the harder examples, and their combined weighted votes lead to a strong, accurate prediction. Let's understand and break down how AdaBoost works for regression, step by step, with intuitive explanations and mathematical insights. Let's get started. Here is our dataset. We have 7 samples, each with a feature x and a target value y. Our goal is to predict the target value y using AdaBoost regression. We start by assigning equal weights to all samples. Since there are 7 samples, each weight is 1 divided by 7, which is approximately 0.1429. Now, we train our first weak learner, which is a simple linear regressor. It predicts the target value using the equation h_1. X equals 2.0 plus 0.5x. Here are the predictions of the first weak learner. The error is calculated as the absolute difference between the true value and the predicted value. Next, we calculate the weighted error of this weak learner. The error is the sum of the weighted absolute errors, which is 1.5719. Now, we compute the weight of this weak learner, called alpha. Alpha is calculated using this formula. For our weak learner, alpha is approximately -2.0. Now, we update the weights of the samples. Samples with larger errors get higher weights, while samples with smaller errors get lower weights. Here are the updated weights before normalization. To normalize the weights, we first calculate the normalization factor z_1. Which is the sum of all updated weights. Here, z_1 is 3.2857. Finally, we normalize the weights by dividing each updated weight by z_1. This ensures the weights sum to 1. Here are the normalized weights. We repeat this process for more weak learners, updating weights and computing alpha at each step. After training multiple weak learners, we combine them into a strong regressor. The final prediction is made by combining all weak learners using a weighted sum. The weights are the alphas computed for each weak learner. And that's how AdaBoost works for regression. By combining many weak learners, each of which is just slightly better than random guessing, we build a powerful final regressor. The weak learners focus on different parts of the data, especially the harder examples, and their combined weighted predictions lead to a strong, accurate prediction. Let's explore the advantages and disadvantages of the AdaBoost algorithm. Here's a table summarizing the key advantages and disadvantages of AdaBoost. First, AdaBoost achieves high accuracy by combining the predictions of multiple weak learners. However, it's sensitive to noisy data and outliers, as it tends to focus heavily on misclassified points. AdaBoost is flexible and can work with different types of weak learners, such as decision stumps or shallow trees. However, its performance depends heavily on the quality and effectiveness of these weak learners. A key strength of AdaBoost is that it focuses on hard-to-classify samples, making the model adaptive. But this focus can also backfire, causing overfitting when the dataset contains noisy or ambiguous samples. Another advantage is that AdaBoost tends to highlight important features, especially those involved in difficult classifications. However, it can struggle if the data contains many irrelevant or redundant features. AdaBoost is generally faster than some other ensemble techniques like gradient boosting, because it works with simple weak learners. Still, the sequential training process can become expensive on very large datasets. Finally, AdaBoost performs well on clean data with clear class separation. However, it struggles with overlapping classes, highly noisy data, or very large datasets where simpler methods like random forest or more optimized algorithms like XGBoost may work better. This concludes our discussion on the advantages and disadvantages of AdaBoost. AdaBoost, short for adaptive boosting, is a powerful ensemble learning technique. It combines multiple weak learners into a strong learner by focusing more on difficult-to-classify or predict instances. AdaBoost can be used for both classification and regression tasks, though it is more widely applied in classification problems. Here is a comprehensive summary table highlighting key aspects of AdaBoost, including its algorithm type, working principle, strengths, weaknesses, and best practices. AdaBoost works by training weak learners sequentially. Each learner focuses more on examples that were misclassified by previous learners, building a strong ensemble model. The key concept is adaptive weighing. Correctly classified points get lower weights, while misclassified points get higher weights, forcing future learners to focus on difficult examples. AdaBoost can handle both classification and regression tasks, although it is most commonly used for classification problems. The base learners are typically very simple models, such as decision stumps, decision trees with only one split. A major strength of AdaBoost is its ability to convert weak learners with slightly better than random performance into a highly accurate ensemble. However, AdaBoost is highly sensitive to noisy data and outliers, as these data points often receive high weights, which can distort the model. The weight adjustment process, where harder examples get higher weights, is the core mechanism that allows AdaBoost to boost performance iteratively. Without proper regularization, too many boosting rounds can lead to overfitting, especially on small or noisy datasets. Compared to a single decision tree, AdaBoost is less interpretable since it aggregates many weak learners, each with different focuses. To optimize AdaBoost, use simple base learners. Limit the number of boosting rounds. and preprocess data to remove noise and outliers for better generalization. In conclusion, AdaBoost is a highly effective ensemble method for both classification and regression. Its adaptive weighing mechanism allows it to focus on difficult cases, improving overall accuracy. However, its sensitivity to noise and potential overfitting require careful tuning. When applied correctly with simple learners and proper regularization, AdaBoost remains a valuable tool for tabular data modeling. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up, subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.